All right, so this actually should say here, so we'll need to correct this. So we'll need to correct this in the slides. This should say linear to logistic, right? So it's kind of like a transition point of the things we need to add. So here we'll talk, we'll recap linear regression, start thinking of logistic regression, and basically the code, the additional elements in our code that we will need to implement the logistic regression algorithm. All right, so yeah. All right, so a reminder, right? A little bit of a reminder. So in this section, we are going to modify and extend our code from the linear regression model. Okay, so that we can implement logistic regression first. So that's what we're doing now. But you already saw a glimpse of a one-layer neural network, right? And a deep neural network already. And hopefully you can see that just by changing that inference function and that loss function, you can start to do that. So in the following code sections, I'll make some modifications so that the new models can be implemented easily. All right, so now I'm going to start to change, become more consistent also in my naming conventions, just so that I know what I'm talking about. So I will use, for instance, here XTF and YTF now throughout the rest of the code to indicate the X data, the features, and the Y vector, the labels. Okay. Additionally, we will use A and B. Now, if A and B don't make sense to you, you can change that to say features and columns, for instance, if that's a little bit clearer for you. But the idea is that, that part of the code, because we know we can calculate dimensions on any tensor, whenever you read your data, you can just go ahead and automatically calculate A and B. All right, so A and B will define the number of neurons in the input layer and the output layer. Remember that the example we just saw looked exactly like this. Right? It's a neural network. Now it had 3 neurons here, right, instead of just the 1, because now it has become a classification problem, and then it has 4 neurons over here because it's the 4 inputs. Right, and it's a fully connected network. So it is something like that. Right, so look at how many weights we have now. Right, so you can do that calculation and imagine how this is going to explode as we start building bigger and bigger data sets, or layers. Sorry. So we already set this. So A represents the number of features. That for iris, that is 4. So you guys already answered this correctly, right? So it's none and 4 for the dimensions of the X tensor. And then for the Y tensor, the placeholders basically, we said it was none and 3 because it stands for the classes Setosa, Versicolor, and Virginica. All right, so now we're going to do here another discussion. Here we have, in the future, we will be using this approach. So this little function here, we will be using to be able to calculate more metrics than just accuracy. So if you remember, we did that example on the performance metrics, right? And what did we say? Accuracy is not, especially in an imbalanced data set, not the best metric to use, right? But unfortunately, the way we have the code right now, it's only giving us the accuracy. And so we need to do a little trick using this function. So the trick that we have to do has to do with the fact that whenever we do output, right? If you remember, output is y, right? And whenever we predict y, this y is going to be one-hot encoded. Right? So it's going to be 0, 1, 0, 0, 0, 1, 1, 0, 0. Right? But intuitively, we want to see it probably like this, right? This is what we're used to. So we would want to see 1, 2, what is this one? 0. Perfect. All right, so that's what we want to do. Because once we have this, if you remember your sklearn examples, we had a nice, very handy function called print stats metrics, right? You guys remember that? The metrics function from sklearn. And what were the inputs to the metrics function? They were the actual labels, right? Y, and then, which I think it was like this, and then the predicted ones like this, right? So it took, this function was written in such a way that it only took a vector, not a matrix of one-hot encoded values, if that makes sense. So we are going to use this little function, since TensorFlow predicts this, just to convert it to that, and then once we have that, we fit it in there, and now, once again, we can get all of our metrics very easily. All right? So it is important to note that this line, where 1 is the x-axis, will be used for performance evaluation purposes. Its use will be shown in the main loop of the code, and so we will see it later on. Here, the YP metrics variable is declared and assigned the index of the max value from output after running it through an argmax function. So basically, we need to understand what this TensorFlow helper function does, right? And so this is the definition of it. So the function tf_argmax is a TensorFlow function that returns the index of the largest value across the axis of a tensor. Right? So this is one of those things that, again, learning curve, right? Learning curve. You have to understand. So for example, instead of just giving it output here, right, now we give it an array, basically, a vector. So we say tf_argmax. So what is here the index of the largest value across a specific axis? So we can see we have 35, 4, 72, and 2. So what is the index of the max value? 2, right? So you guys got it right. So 0, 1, 2, 3, right? So, and that's what it returns here. Do you see that? Okay. You can also define an axis like so you can have an axis that looks like that. And that would be this. So now, since I think you do understand argmax, if you apply argmax here, right, we're saying that across these axes, this axis, we would get the index of the maximum value. So for the first row, what is the index of the maximum value? So the index of the maximum value. Yeah, for the first row. 1. It's 1, right? Guys? Okay.
First row or the first column?
I mean this row, the one I underlined. It's.
What did you underline?
Oh. Well, I'll do it again.
Oh, at the very top. I'm sorry.
Yeah, the row, the first row.
Oh,
Right.
You're talking about the actual example.
Yeah. Yeah. It's one-hot encoding, but these little tricks, which are really abstract when we read them, actually make a lot of sense once you understand what's going on. So I look at output, right? I take output, and I indicate that I want index 1, right? So the rows. So again, I'll repeat. So using argmax, what would be the index of the maximum value in row 1? 1. Perfect. Row 2. This one I'm underlying here. What is the index of the maximum value in that row? 2. Perfect. What is the index now in the third row of the maximum value? 0. Do you see how perfectly, whereas before you went from here to here with one-hot encoding, now argmax, just that function there, takes you from one-hot encoding back to the regular vector. Yes?
If you had an instance, I don't know if this is possible, but it would be like 0, 1, 1, would it spit out both?
You wouldn't have 0, 1, 1.
Okay.
You can't have that by definition. I'm sure, okay, well, let me rephrase that. I'm sure you can figure out some way, but in general, that's not what you want, because it's, one class or the other or the other. Does this make sense? All right, so hopefully it does. So why do, again, I'll repeat, why do we want this? Is because we don't just want accuracy, right? We will want, this one hot converted to this, and we know already that we have a nice function that return all the parameters that we need. So we will do this. All right. Are there any other questions with
So
this?
that
Yes.
example at the bottom is returning two values, not a single position.
Well, it's similar to what we just did, right? 0, 1, 2.
So it's two for the
Two.
first one, 0 for the second one, not position 2, 0.
It returns the index of the maximum value. So the index of the maximum value here for the second line is 0. Perfect. Just keep in mind, okay, argmax doesn't just work for one-hot encoded matrices. It works for all kinds of matrices. It just so happens that it's the perfect mechanism for one-hot encoded.
So it wasn't clear at first if it was returning the singular point that's the maximum in the entire matrix or per row.
It's per row because you specify,
I
yeah.
know that now.
Yeah, sorry.
First
So
I thought it was returning the singular point that's the maximum value in the entire matrix, which I was trying to map that.
I see why, because of the previous example we did when we didn't specify an index. So I see your point. But here, so this is just an example I wrote, but this is definitely in the code, how it should be. So you specify the dimension, or the axis of it. All right, great. All right, excellent. So that's one thing that is going to make our code clearer as we go forward. So keep that in mind. And here it is. So we create our XTF and YTF as placeholders. We use this one for performance metrics. You can give this some better name. I don't know why that name is there, honestly. You could say from one hot to single vector, output, something like that. The training function, for the new models, we continue to use the training function. Remember, there were 4 core functions that we previously defined. Although very little change, it is important to mention that the optimizer and learning rate can be changed. You can play around with those, and that there are many alternatives that could be used. So there's, in fact, a list of gradient descent, atom, but there's other ones. So a lot of research has been done on this topic, and it is currently an open and ongoing research field. So there's still changes to come, I'm sure, on this. Okay. All right. So that's that. So as you can see, this function we just use as is. This is just the same one that we had before. Nothing will change there. Now, the other thing that has changed now is that it's not a linear regression anymore. It is a supervised learning. So that means we're trying to predict classes. We need to have labels and all of that. We need to have some kind of a way of evaluating our algorithm. So in linear regression, we were training to predict any kind of real valued number, the housing price. From this point on, we are going to try to focus mainly on classifiers and predicting classes, right? Therefore, in supervised learning, we will usually have real labels and predicted labels. So you could say, ypred and then ytest, right? So they're going to be in there. So our models will predict labels now, and we will need ways of comparing them to the real labels. Okay? The following function is a way to evaluate actual and real classes per sample, YTF, against a predicted output. Okay? Per sample in the test set. Now again, this function will have a lot of additional TensorFlow helper functions, so we need to define those as well. Because, TensorFlow is all tensors, it's all about efficiency, and so these are the fastest ways of doing things. So we compare the two sets of one-hot encoded labels with TF equal to measure the accuracy. So remember, this is just for the accuracy. So what is TF equal? So that's another one of those functions. So the TF equal function returns a vector of Boolean values. all right, that compares the values in two tensors of equal dimensions. So that's handy, right, when you're predicting actual versus predicted. That's very handy because it's going to tell you if there's a match or not. So given x and y, we can do TF equal x and y, and this is going to return what? So we compare. These are not equal, so that's false. These are not equal, that's false. These are true. Or equivalently 0, 0, 1. Right? And so that's what that function does.
So does it care
Oh,
if
yeah.
it's, real or float? Like which line
Does
you
it
want?
care if it's real or float? It might, actually, so you'll have to test it. However, I would think that most of the labels are always going to be some kind of an integer and not a float. That's what I would say. Because remember, it went through one-hot encoding, right? Do you remember that? Oh, actually, let me answer that in a better way. If I use the function that we just talked about, argmax, remember the definition. It returns the index of the maximum value. There is no float index. Right? So, all right, so now we have this one. All right? We can continue then. Are there any questions? All right, so we can continue. So now, remember, in linear regression, we had nothing like this. Right? All we had was a way of predicting the values. Now for classification, we are defining an evaluate function. Now the evaluate function takes these two parameters. So what are these two parameters? What would you say they are? The test data, right? The labels. So this is the test labels, or the whatever the labels are, the real, let's say, or actual labels. And output is what? Exactly, the predicted, because output comes from the inference function, right? So this is the predicted. Do you see that? And so now these are currently in this function one-hot encoded. So that's the complication, right? That's the complication. So they are like this, something like this. 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, 1. You see that? That's what we are giving it because it's TensorFlow. And the labels are one-hot encoded.
Don't you have a duplicate on the left-hand side?
I have a duplicate on the left-hand side.
Don't you have two twos there? Oh, but you same break.
What do you mean? I'm sorry. I have a...
On the left-hand side, you've got
Left-hand side, you mean this?
yeah.
That's it predicted class 1.
Okay.
And over here, so I should say, this is the actual, and this is the predicted, pred. You see that? So now we're going to compare, but they're one-hot encoded. Because, questions? Because it's TensorFlow. And that's how things are done. All right, so now look at this function here, right? So this is what I keep saying, right? So that's that learning curve. It makes no sense if we just look at this like this. Because we are not aware that everything is a tensor. But if we start to understand the functions, then it should make sense. So this could be a really nice quiz right here, right? Explain what is happening. So what do you think happens here? So let's analyze it. We have these two, and then if you notice, we have a TF equal of two terms, right? A and B, A and B. So let's forget about TF equal for now, and then let's just focus on this one and this one. We already know the definition of TF argmax, right? So what are these two functions doing? TF argmax of output. Which one is output here? This one, right? And then which one is YTF, the real? That one, correct? So now, if I apply TF argmax to output, what does it return?
Value the one in that row, which is going to be 1, the index of it.
The index of the maximum values, right? So it's going to return 1, 2, 2. Perfect. And then the other one is going to return what?
102.
102. Do you see that? So now it seems trivial, but before, without knowing it, it seems complicated. So now that we have this, then TF equal is really TF dot equal is like that, right? Remember, we just defined this one as well. It returns true or false if there's a match. So this would return 1, right? True. The second one is 0. Yep. And the next one is 1. Perfect. Do you guys see that? All right. And then once we do that, now we send correct prediction through a cast. That just changes it into float. Right? Now we want to change it into float. And now reduce mean, if you remember, calculated the mean of this. And this is a nice trick to calculate the accuracy, if that makes sense.
And the 1 in there for output comma 1 just means it's the position of the axis, right? So if I had a
Yes.
0, comma 0, it would be down the column.
Right, right. But because they're one hot encoded for this particular case, they're usually 1. Yes. Now this is important even if you weren't using these, because you can do other operations and just you're writing instead of writing a whole bunch of for loops with huge amounts of data, you do this efficiently in the tensors. Right? So that's one of the computational advantages of this. Are there any questions about this code, guys? All right, so it seems like everyone understands it. So let's move on. So the core functions, right? That's the other part of the code that we just saw. So now we are ready to once again use the functions inference, loss, training, and evaluate to define our model. This is where the magic, right, will happen, and where the code will be specific to the algorithm and the architecture. So you should be excited, right, that now you're close to writing a deep neural network, right? We're almost there. Since this will vary based on classifier algorithm, each algorithm will be addressed in its own section here, right? So right now, I'm only doing logistic regression. For now, I will simply define how we can call the functions. All right? So here it is. This, once again, is the core functions. If you remember, just like we did before with linear regression, we had the inference. It takes x, right? Now we plug in A and B just to make it a little bit more convenient, right? Since this is where we're specifying, remember in the inference, we specify the input layer and the output layer. This is the loss function, right, that takes in, so maybe I should do, the loss function takes in this output, right, the predicted, and this YTF is coming from the placeholder. So this is our real data. Then remember cost then plugs into the training. That's what we want to optimize, that loss function. And then that's it. And then when we do the evaluation, we call output again, right? Our output, and then we have the YTF, right? This time for the test set. Right? And you guys can see it also in the computational graph here, kind of the same thing. This is the inference function part. That's the inference function part. And then here we have the loss function part is this one, right? So optimize the cost, all right? Output, which is compared to this YTF, right? The real labels. All right, so that's just pretty much the same computational graph we had before. Questions? All right. So, deep neural network. If we were defining a deep neural network with several layers, remember, logistic regression only has that. It has 4 neurons in this layer, 3 neurons in this layer. Right? That's what we did in that inference function. But if we want a deep neural network that now has multiple layers, we can define the function calls as below. So we can see that here. Notice it's pretty much the same thing. Still train, still evaluate, except that now I call, instead of inference and loss, I call the functions inference deep and loss deep. So now I had to create two new functions that capture this idea of the architecture, if you will. So the structure of the core functions does not change. All right, so the structure of the core functions does not change. What's going to change is what's inside these functions. All right? So the important aspect is to keep in mind that the structure of the code is mostly maintained, and that the only thing that really changes is the internal definition of the functions inference and loss in particular. Right? So that's what changes. So the only two functions we change to go from logistic model to a deep neural network are these two that I mentioned. All right? And I talked about that. All right, so hopefully that made sense. Are there any questions about that? The next part that I'm going to talk about now is batches, which is one of the questions some of you had. Right? So if you're doing big data, you're going to read, lots of data, right? But you want to read it in batches, in chunks. Okay, so, all right, so let's move on to the next part, okay, which is batches. All right, so in the next code section, the session declaration and initialization are defined. This part is the same that we defined for linear regression and is consistent with logistic regression. So that's not going to change. All right. Now, as you know, I've mentioned this many times, right? The advantages of deep neural networks and TensorFlow in particular is that we can now read in massive amounts of data because we have this mechanism of loading data in batches. So loading millions of records directly into RAM memory may not be suitable for most big data challenges, right? So we can't take that approach. So instead, to be more efficient, we can load the data in batches. So that means we're going to take our data set and divide it into bins of size n. Right? Bins of size n. So we're going to look at that. Oh, yeah, please.
So you said we should do the split before we create our batches. So we can take a random sample of 80, let's say.
That is correct. I said that.
We don't need to load it into RAM to do the split.
That's true. Okay, yes.
If you have millions of records, then
I see where you're going with this. So what you can do is build a model just on the set that you have and apply it in batches to the data. You could do that, right? Because we learned that normalization is actually training on some set, right, and then applying it to all the data.
so for each batch.
So I mean, that's the only solution that I can tell you. If it doesn't hold, if it doesn't go in memory, what makes sense? Grab it, the largest subset that fits, train that normalization on that, and apply it in subsets to the data set.
So it's not that you should take each batch and split into a training and test.
No, this is just different for the normalization. I see your point. You're saying, okay, I took care of reading it in batches after it's normalized, but if I have to normalize it, if it's really large, the normalization function won't be able to do it, correct? That's your...
Normalizing and splitting. I mean, there's stuff that we did to the data before we turned it into batches. Right?
Yes, I agree. So what I'm suggesting is, for that, if you don't have enough memory, train the normalization algorithm with just a subset of it, and then apply that. It's not a perfect solution, but it's a solution. Do you see that? Yeah. There might be, all of this, there might be better, more efficient ways, right, of doing things. The other thing is, so there's two things you could do. Run it without normalization, right, and see what you get. Also build a normalization algorithm, just not on all of the data, and see what you get. There might be a third alternative, the efficient one. I'm not sure what it is. So the question would be, does TensorFlow have something like that? And it's a good question. I just haven't thought about it. All right? Any other questions, guys? All right. So we're talking about batches, I believe. This we already mentioned is the same. So batch size codes, right? So this, again, this is only for reading the data. So in this, I showed how this can be done. We will need to define the size of each batch, and that's something that you can do arbitrarily. But I did provide the example that we had picked a batch size of 100 and just took longer to train the model. So maybe the largest batch size that you can define for your environment is good. We also need the size of the train set. So to do that, we can basically take xtrain normalize shape of dimension 0, right? What does that give you? Do you think? The number of rows, right? That gives you the number of rows. So that, in essence, is the number of samples in the train set. All right? So a lot of the complexities with TensorFlow, hopefully by now you realize it's just this. Because everything's a tensor, you need to figure out the dimensions, and you need to have this insight of how to get shape sizes and things like that. So this gives us the number of rows. And now if I have the number of samples and I have a batch size that I've defined, I know the number of batches that I need, right? Are there more efficient ways of doing this? Probably. This is just an example of how it can be done, right? So it's in one of the code examples that we've provided in the labs. All right, so here is the two functions that you could have in there for batch calculation. And now, since you're going to do batch processing, you're also going to need to slice the data. All right, so we're going to do a little bit of slicing once again. So we're going to read the number of batches from the train set. All right, so let's see the code. And this is basically the code. So now we have the number of epochs, right? We print out the current epoch, and now this part here is where you read the data in batches. Okay? Now keep in mind another question like similar to the one she made is that you can't load all the data from the hard drive into RAM, right? So in that case, you would have to read some of the data from the hard drive into RAM. Then from that, read it in batches. Next iteration, read another chunk of the data from the hard drive into RAM. Read that into TensorFlow in batches, and so on. Does that make sense? Okay. All right. So, okay. All right. Now that we have the definition of num batches here, right, this is really our code for reading this. So as I said, I just came up with something that would illustrate this in a very easy way. Obviously, there might be, you guys can program this, I'm sure, in a more efficient way. So this is based on the batch index here, batch n, right? So initially, batch n will be 0. So 0 times the batch size, which is 100, is 0. And then we have the ending index, which is 0, plus the batch size, which is 100, so that would be 100. Right? So having these start and end indices now allows us to slice out some of the data. Right? So I'm going to run train up, and the feed dictionary, remember, you take xtrain normalize and you plug it into xtf, and you take one train one hot and you plug it into ytf. Those are our two placeholders that store the data, right? That store the data. But we are doing this in batches, so actually from those X train and Y train, we slice out the information. So here, if you look for X train normalize, it is 0 to what? 100. 0 to 100, and then what does that mean? It means all the columns, right? It means all the columns, but only the rows from 0 to 100. So if we had a data set like this, we have sliced out that chunk. Do you see that? Okay. And then the next iteration, we're just going to increment. So now batch size is going to be 1. So 1 times batch size is 100, and then 100 plus 100 is 200, so now we can slice out the next chunk. Yes, sir?
You're doing the 100 row twice?
I'm doing batches of 100 rows. Yes,
So
correct.
you're doing row 100 twice, right? So you did 0 to
Well,
100.
that is I mean,
Is that a problem?
technically no. I mean, the one duplication out of millions, might not be such a killer thing. Especially if, okay, so if it's 100, if I made a mistake in this, and you pointed it out, if my batch size is 100, then it's a bit of a problem, because it's too many duplications. But if my batch size is, say, 100,000, and there's one duplication in there, that's not going to kill our algorithm, right? So you're talking about 4 million records. So how many duplications do you have there? It's not optimal, so we would obviously want to fix the code to address that if I've made this mistake. Just figure out a better equation.
Oh, is the end exclusive? Oh, okay.
So there's no duplications? Okay, great. So thank you. So there wasn't any. But your point is very valid. I like that question. And as I said, if it's very small, you start adding too many duplications, which is not great. We saw that actually when we did that label thing, right? Yeah. And so we've already seen the effects of that. But the bigger the batches, not too bad. Good question. Any other questions, guys? So that's it as far as batch processing. I mean, I don't know that there's definitely other ways of doing this, for sure. More efficient ways, better. This is just, as I said, for understanding of the student. Any questions? All right, good. So the other thing is, so now that we are remember, so what part of the code is this? This is the main for loop, right? The main for loop. So notice we read the data, we do session run on train hop. So by now you should know that just means we're building the model, right? We're training the model in batches. Then we do this, right? So now we're going to run session run on eval op. Eval op is that function that we defined to calculate the accuracy. That TF equal. And then we calculated the mean of all the trues and false. However, I said that accuracy is probably not great, especially if you're looking at imbalanced data, right? So instead, I also want this variable. This is the variable that I can use with my performance stats metrics function from sklearn, right? The one that takes the one hot encoded and just creates the regular vector that we're all used to. So if you look at this, I have a new technique now. When I do a session run, if I provide a list, I can actually run 2 nodes at the same time. Do you guys see that? Here, I'm doing eval op, but I'm also doing YP metrics. What was YP metrics? Anyone remember? So YP metrics was,
accuracy.
it was actually,
Flattening the
this one, right? Do you guys remember this? Going from one hot to not one hot. Right? So this TF argmax, so it's YP metrics over here. So that's going from here to here. Right? And so that, notice now, even though I introduced it before, I'm showing you now where you can use it. So if I go back to my code segment over here, YP metrics is now that function, and so that gives me right result metrics, which is some weird name. You could have used a more original name. Notice that the feed dictionary that I provide is for the Y test one hot and X test normalized. So the keyword test. I didn't read this in batches or sliced it. Okay. So obviously here you can modify this in some way if your test set is really large also. Does that make sense? The idea would be, okay, so I guess this is a question for you. If you have 4 million records for training, is 100,000 records for testing enough? Or do you want to have still like 30%, 70% swap? Maybe not for balanced data? Okay, so if that's the case, then we might need to modify this a little bit to read also that in batches. And then, but if we read in batches, what do we have to do? We have to create a list, right? For this one is this, for this one is this, for this, and then maybe take like overall. Do you guys see that? So when you do big data, there's challenges. Now there's more of, reading things in parts. Okay. This is obviously, if I had all that code in here, it's going to make it even harder to comprehend, right? So this is the bare bones, I think, most simple that we can do. All right, so hopefully it made sense that we created Y result metrics, right? Now notice that we print out result, and that's just a thing that you saw, that 37, 47, all the way to 87. But now YP metrics, so let me clean this up. This YP metrics, which is that from one hot to the normal one, is now going to be used there. And that's our handy function from sklearn, if you remember. The one that prints out precision, recall, F measure, and the confusion matrix. So once again, you have those metrics there. All right, so now you should know. So this should also be a quiz, and you guys should know the answer. Look at this Y true and that Y true there. So now one important thing. I don't know if you're very if you really look at details, but there's a slight difference here. Do you notice what the difference is in this argmax function? It's a numpy. It's not TensorFlow, so it doesn't need a session. Right? So it's good observation. All right, notice this is a numpy. No session needed. Because numpy has the same ideas, right? Argmax. So what do you think you're doing here in this one? Your data was what? Whenever you gave it the Y-test data, it was one-hot encoded, right? So we have to reverse that and make it not one-hot encoded. So that's what's happening here. And then this Y true, which the name implies, these are the actual labels. Oops. Go in there. Do you guys see that? Are there any questions about this? That's it. No. So it's clear? All right. So that basically allows you to print out your performance metrics. So now you can, like what you will do in your labs. I even have the prices here. Right? So who's going to win this amazing hat, right? So, so now you can do, you will be able to apply this data set in the fraud detection problem tomorrow. All right, and so, but you can use our code. Obviously, you just have to maybe tweak it a little. Okay, so yes, sir.
What size is the hat?
What? I think it's adjustable. So.
Okay, we got to make sure we get certain things.
Yeah, there's also a prize for originality. So whoever comes up, maybe not wins, but has the most. This is really nice. I have one of these. So that's for originality. All right, so hopefully this is starting to make sense. As I said, once we get through logistic regression, neural nets and deep neural nets, slight changes. And so, it's all very consistent. All right, the last part is, you might want to print that function that I mentioned, right? That plot metric per epoch, right? That's that function that you saw. And so here I'm just doing it, like when the index hits like 1,000 or something, I just want to see that graph and just kind of picture where it is, then it, and so on. You could do those tricks with the mod or whatever, right? And you can also print it every few thousands or whatever that is. But that's it. So this is our main loop. All right, so I'm assuming if there's no questions, I'm just going to keep going. So this is a summary. Actually, this is a good point. Just kind of see where we are. We looked at batch processing. We looked at some of the variables like epochs, etc. All right. So now that you have this, let's do this. So let's do the lab. All right. So let's try the lab so that you get to practice a little bit, and then after you know TensorFlow, I think enough at this point, right? So you have a classifier now in TensorFlow, right? You should agree about that. You have a classifier called Logistic Regression. So why not try Logistic Regression and Weka and sklearn and see some results, right? So we're gonna do that, and then after that we're gonna continue with our discussion. So the next lab then is the one in the schedule. Let's take some time to solve it. So we are. So this one, KDD small. All right. So now.
4 o'clock today.
Yeah. I mean, do you guys want to wait until 4 o'clock and do it then?
No, I just want to make sure I got the right one.
Yeah. I'm just saying, if maybe work on this, wake up a little, and then we can continue with the slides. It's up to you. You want to wait until 4? We can do that. No? All right. Go ahead. So work on this lab, okay? Keep in mind the plan for most of tomorrow is to do labs, but we still need a little bit more code. We're almost there, but we just need a little bit more. So here, whereas before I think we've always provided you with one single file, right? And then you have to do the split in the code. Now in this case, we're providing you with 2 files, a train test and a test set. Okay? Now keep in mind some of this code should be in your VMs. Tingyu, that's in the VMs, correct? Yeah. So it's already in the VMs. All right. So, but what I want you to do is try to implement the logistic regression algorithm, for instance, in TensorFlow. So let's read through the lab. So intrusion detection. So we call this intrusion detection small because we took the 4 million KDD and we just made it smaller so that it fits in Weka. It doesn't take 20 minutes to run things, and we can do it kind of quickly. Tomorrow, hopefully, AWS will work in the morning, and we'll do it with 4 million. So what is KDD? It's an intrusion detection lab. So this lab is to implement a binary classifier to distinguish normal connections from attacks. All right, you are required to read the data from the training set, which has 2,799 records, and the test set, which has 1,199 records. All right, so remember the data looks like this. So you have, the features, duration, protocol type, service, flags, source bytes, source destination, or destination bytes, etc. So you are required to implement it in 3 ways: using the machine learning software Weka, writing a Python script with the use of the package sklearn, and writing a Python script with the use of the package TensorFlow. And you can use deep learning, even if you don't understand it, because the code is provided. Try to see if you can figure it out, or at least with logistic regression. We have an example of that already. The lab environment, the students should have access to the Linux system. Your VM is fine. Weka. The environment for Python is required, as well as the packages NumPy, TensorFlow, and sklearn. The lab files that you need are train kdd_small.arf and test kdd_small.arf for Weka, and train kdd_small.csv and test kdd_small.csv for the Python scripts. So those should be in your VM in the kdd_small directory. The last column in the class value is the class value. The other 41 columns are the features. So that already tells you this has 40 features or so. But you want to make sure exactly how many it has, right? And you have now functions, like the shape functions, that can give you those values. Oops, I'm sorry. So here is the steps, basically, on how to open Weka. Now, if you notice, in the past we've always given you CSV files. Now we're giving you these .arf files. What do you think these are? Why are they called ARF and not CSV? Is it the same data? What's the difference between CSV and ARF, do you think? They're the same data, actually. It's the exact same data. So what could it be?
Like an array or something?
What do you mean by that? An array.
Like instead of, I was just going off of the letters and guessing maybe it was an array because it starts with AR.
I think what you mean is that the format is different, maybe,
Yeah,
which is the case.
differently
Yeah.
formatted.
So exactly. So the data is the same, but it's a different format. CSV means comma separated. If you open the ARC file, you will see that it just has a different format. And it's actually the format of WECA, the WECA format. Yep. And so why did we do it that way? Because that's what it wants when you give it two separate files. Now, I already showed in one of the lectures how to do this in WECA, right? I think you asked that question. So you guys should know how to read two separate data sets and apply the model. Okay? So these are the instructions. So import data in the train KDD small arf into WECA using the Explorer. The files of type should be specified as arf. Choose the proper classifier. Obviously, you need to make sure that the values are numeric to nominal. You want to give a scan on the data, right? You want to open it, make sure everything is good. If it requires some cleaning or pre-processing, I don't know, right? That's kind of what you have to do. Then you can choose classifier. So J48, remember, is a decision tree. We've already tried that one. You need to specify the test option, right? So how do you do that? All right, so hopefully you remember. Here's some hints, right, of how to provide the test set. Then here's some hints on how to run a model, right? Now, should you only run decision trees? I know that some of you, for instance, we had this discussion, right? Categorical data never use KNN, right? So that's what you guys said. But at the end of the day, maybe try a few, right? Try a few classifiers, the ones that you think you should use. I will tell you, I think, if this is KDD, I'm almost certain, double check, it has source port and destination port. All right, and those are that categorical discussion, and so it's your choice, right, whether you use KNN or not. But definitely try a few classifiers. So does the WECA part make sense? All right, I think it does. Now, the second problem is use sklearn. So in this exercise, you need to implement several classifiers with the use of sklearn. So you have the code already, right? Just read the data, read the features and class values from train set and test set with the proper method. So here's a hint of how you can do it, right? So gen from text, remember, I believe we've already used that. Just keep in mind, now we're reading things from the outside, right? And we still need to have 4 sets. X train, Y train, X train, Y train, X test, Y test. So that's 4. So here's a few things that you need to be aware of. Now, there's the use of label encoder, right? You should remember what label encoder does. It basically converted words into classes that are numerical. So see if you need that for the features as well. The standard scaler, if you remember, that's for normalization. So you should know that. Here's an example of how to do like support vector machines, for instance. And then this is our print stats metrics, right? This function is actually very handy. We can use it. We just saw that we can also use it with TensorFlow outputs. Okay. So implement the classifiers based on logistic regression, support vector machines, random forest. Just pick a few. So at the end of the lab, you want to compare WECA to sklearn, right? All right. So problem 3 is one that we can now start to do, right? Because I believe at this point we have enough machinery an understanding of TensorFlow that we can at least do logistic regression, or try to do it. So the same thing applies here. In this exercise, you will implement an artificial neural network based on TensorFlow. Here are the libraries. Repeat the same steps to pre-process the data as exercise 2. Read the data, do standard scaling of the features, and encode the labels. All right, here's how to read the data, right? A little bit of pre-processing. We already know about these parameters, right? You have to do one-hot encoding. It's your choice whether you use the TensorFlow one-hot or this one. Get the dimensions. That's probably a good idea. You can plot. It'd be nice if you plot this, right? You know, get that feel of how many iterations it takes to learn. And then this is the deep neural network stuff. So if you can figure it out right now, great. If not, that's okay too. But at least it'll make you think a little bit, and it'll help us out when we discuss this more in the slides. Okay, so that's really the idea. Instead of listening to me, you kind of try to figure it out on your own. Keep in mind you can at least do logistic regression because we just did that. Print stat metrics, it's the same there. All right, here's the code as well, and that should be it. Right, then what to submit? Well, remember, this is like when we give this for a semester class. So you don't have to submit anything. However, you should keep some, write them down on a sheet of paper or something. So it'd be nice if somebody can tell me, like, oh, the best classifier was this, logistic regression or whatever. And the accuracy was this much. Okay? So, does this make sense, guys? Okay, hopefully it's not too difficult, but let's see. Let's kind of test the waters here and see how you do with this lab. So it is currently 2:50. So we'll take a break at 3. So we'll try to give it from at least 30 minutes after the start now, take the break, and then at least 30 minutes afterwards. Given that you do have the code already, I don't think it should be too difficult, but try it out. Are there any questions? You can work in groups also if you want to ask questions, to your people sitting next to you. That's okay too. Please raise your hand if you have any questions. Yeah. Yeah.
It's 532, I put like the number of.
You have to read in the whole data, iterations rating, and then you split one, and one of the
Third,
Anyways, 532.
Yeah. Okay.
Just see
So
some-
great.
part 32. Okay, I heard it.
I was curious.
Yeah, me too.
Word batch.
Does the batch have a combination of training and testing? Each batch is a combination of training and testing.
Not usually.
Okay, so if you're reading over the bit, then you split the training and testing. Then you just make batches with the training set. Or you do this flow. Then you run a random sample. Then you run a random sample.
Not at this time, no.
That's not good.
We can talk about it and see. Any charters, questions? Questions over here? Questions? Ah, yeah.
What if I could use the Tensorflow one
Well, I know the random sample can't come before you read everything, because you were telling me that there's this place where you have 64 gigs, and then on the GPU only has 6
So where
gigs.
are you?
Read everything in the 64 gigs. And I'm asking you, at that point, do you do a split between the training and the testing, or do you turn it into 6 gig batches? Okay, so then your batches are a combination of training and testing, or the batches are just the other training set.
Okay, so if I choose these stills. Okay, so if I try to here it works. So if I try to run it with a different data set, what do
When they're both not.
Right, so in here, you're still not yourself, right? Because they're coming in from wireless, they're going to test.
I wanna work on the left,
Try
I think,
to
because
one from the same file, use the split. So we can use just split with the one hot.
Oh, can you do it before you do the one hot and then do the one hot?
So I tried this thing
Remember, the one hot is only applied to the Y, right?
Yes, so I'm only applying it to Ys.
Yeah.
So since with the split thing, since you apply it to different arrays, X and Ys anyways, then one hot Ys.
But I provide, so for, are you talking about for this KDD small? We only provided,
It's working, it's got different.
for KDD small, we provided the train set of the
Yeah,
test.
so for that one it works using the Tensorflow overlap.
Okay.
Some of the other ones, the older ones that come back up.
Okay.
Those ones don't work. Because they have we're splitting up the test training sets. It doesn't like the tensors don't have the length argument, and they don't have
So I would do the train test split first, and then the one hot.
I started.
Okay.
Is that the order you follow?
Modifying that for code.
Because I don't know if I understand correctly, train test split may not assume that you're giving it one hot code.
That's what I'm doing.
Why?
Whether that's the way or not.
You know what I mean? Like it's an S.
I'll let you
First
know
of all, it's an
if
S
it's
scalar function, right? It's not a.
That's what I end up doing. It looks like it's working. I just have to learn how to
Yeah.
the training.
Yeah. So that's what I would say. That
Okay.
remember you're using an S scalar function.
Yeah.
That doesn't assume one time coding.
Okay.
The only TensorFlow is one time coding.
Got it.
Yeah.
Okay.
All right. Any questions over here? Questions, guys? Here? Questions? Questions over here? Great. So let me know. As I said, kind of trying to give you an open period of time so that you can actually try out things, right? Little practice. Remember that all these algorithms are in your flash drive already, right? So you can just easily navigate to the flash drive, KDD small, and everything should be there. Read the code. Code should start to make more sense now, especially the TensorFlow one, given the explanations. Actually, I've given you a lot of the code. What we're doing next is more like theoretical, as opposed to so much TensorFlow.
Can I ask you about my
Yeah,
My results are too good.
sure. Too good.
Yeah.
Mine were too good too.
Okay. Yeah, my results are perfect. Even on the
This is remember it's KDD small. It's not like the and then actually KDD even big does really well, right? It's not a difficult data set per se. That it's just for academic purposes. I mean, it's MNIST and all those data sets do really well. Iris. Yeah, I mean, hopefully tomorrow's will be a little bit more challenging because it is very imbalanced. But KDD is an academic data set, so it should do okay. Even does naive Bayes even give you like 100%? Even naive Bayes.
I didn't.
So I got like 99.96.
Yeah. So I mean, it's just a very easy to classify. I mean, yeah. So
I
that's what it
did
is.
IBK and
K and N, okay.
K&N.
And they all do okay, right?
They have 48.
Okay. So I think right now it's more about not getting results that are in the 70% range, but instead it's about like making sure you get KNN to work, Weka to work, scalar to work, TensorFlow to work. That's really,
Because I got perfect scores when I tried to run against my test set. I got a perfect score again. I wasn't sure if I was doing it correctly or not.
in which program?
And like
Okay, so I can look at it and see what you did.
so I ran it and I did the right click and rewrote the model and test it.
Okay, so do it again. Do it. Let's see. Do it again. So do one. Open a file. Check the label first, just to be sure it's okay. It's nominal, right? It's very some balance. Yeah, what are those numbers? Okay. Yeah.
So it ran.
Okay.
Winning results now.
Okay.
Compared to.
Yeah, that's right. That's it. That's the right procedure.
Logistic.
Yes. Yes.
Okay, I did like the simple logistic on there, and then logistic.
Sure. Yep.
I'm gonna ask her that stuff, just make sure, because I would
Yes.
like add two functions and modify
Yes.
to the calls. as well.
Yep. That's correct. I mean, that's the correct pipeline. It's just the data set is very easy to
I
classify.
think the thing is just like you copy it.
No, you did the right pipeline. It's just our data set is
I
just.
just didn't realize
Tweaks.
that he was so good at that. I thought it was in the folder at first.
Oh.
And I was like, yeah, I can just type and then he doesn't know.
Yeah,
Sure, yes, that was
yeah.
right? So, yeah, exactly, right? So in all the data sets we've done, iris, MNIST, they will always do above 90%. Tomorrow's phishing and fraud detection, and they're still going to do well. Yeah, so if I could give you something messy, but I don't know what, do you want that? Do you want me to just to get the experience of something really messy? Is that what you, I mean, I can do that. Okay,
Like the challenge.
but something that really
Yeah,
does
yeah.
really bad.
Like the problem I had here was I thought I can't put in the right rock and it keeps coming out perfect.
I can do that. I can-
Who did something wrong if I did?
Yeah, if it keeps coming out perfect, I think I'm not sure.
That's fine, that's fine. So let me do that then. I will add another data set that I think is really like noisy, like Twitter data or something. But also there, it's never going to do really well. It's going to frustrate you. But okay, that's fine.
Right.
That's fine. That's fine.
But this is a good starting point.
I think so because I really just want you guys to learn how to read the data, get your results. But I will provide that. That's fine.
Just a question.
Yeah.
If I'm using 90 days, does it just ignore the categorical data? How does, like with Weka? So
Does it
level-
just ignore the?
So for example, when I do 90
I don't think it ignores anything.
But how does it treat the categorical data? Is it just like when on coding? What's going on?
It doesn't convert it. So I think, okay, so if I understand your question is you have one column with categorical data. And you think that, and you're asking if somehow magically Weka will figure that out and make it into one hot encoded, right? That's create new features of it.
Because for 90 days,
It does not do that.
So how does it, for 90 days, how does it?
It just treats it as a variable with its number.
But there's no numbers, there's just words.
So
Like protocol, think of protocol, for example. It's not
yeah,
numbers,
so it might just treat it as 0, 1, 2, 3. It does not one hot. It doesn't. I understand what you're asking. It doesn't do that stuff. However, you could do that stuff. There might be a filter in the filters here that basically says grab this column and make it into what you just said, one hot encoded. So you would just have to find the filter, select the column that you want, hit on it, and now it'll probably get rid of that column and create all the ones that you were looking for.
Okay,
If that makes sense.
right, so just so I'm clear, so the categorical data, which is to be encoded in a naive way, where we just 1, 2, 3.
It's just going to treat it as, like naive base will work with words, right? So if I have the word happy or, is it present 0 or 1? So it's kind of the same thing. Now if I have a categorical 1, there's a value. So the way that,
But that's more like treating the one hot encoding is out.
but that's for words, yeah, for words. Here it's not going to one hot encode it. It's just going to treat that one column as a one column with its values there.
But how does it incorporate
In the model?
into the naive base algorithm? How does it
I didn't cover the lecture,
Yeah.
but it's in the slides here, and I did do the video before.
Okay, I just,
So
with categorical
do you have, okay, so I'll show you. So if you look over here, so we didn't have time to cover this on Tuesday, but I did do a video of it already, and here are the slides. So this is the algorithm for naive base using one hot encoded words from NLP. And so,
Right, and that's where you have one on hot encoding and with the next data that you're going to have this single feature encoded in categorical data, so I don't understand how naive base works.
I mean,
Unless
it
something has to be going on with it. So
I don't believe, but
like something has to be
I don't believe, I understand what you're saying, but I do not believe that it automatically figures out that this is categorical and it one hot encodes it. It just treats it as one variable.
Well, it knows that already because it's not building it up. It knows that it's not there because that's the data type.
It's nominal, right? Yeah.
So, for example, protocol is not building up.
Yes.
So it knows it's categorical. It knows it's not pairwise. And we can talk about it later. I just
Yeah, I'm thinking
it's
of.
something I
I'm
know.
thinking.
It was more
no.
curiosity of how it deals. It either ignores it or one not encodes it or there's something different going on.
It's a multiplication. So it's so naive base calculates the probability of a thing, a sample, being a category. Right. So if there's 3 categories, it's going to have 3 functions, where it takes all the words and it multiplies them based on the frequency of that occurrence of that, right? And so let me bring up the slides and
Okay.
let's see if you can spot on by yourself the question you're asking. So let's see. By the way, you guys can take the 15-minute break, right? So we're kind of in it 3 to 3:15. So
What's that?
14 years.
so this is naive Bayes.
Where'd you get?
So this is the algorithm, right? So it's got the features there and the classes. But you take a probabilistic approach of it, all right? So, kind of like a count. So what are these probabilities? So I'm going to give you an example just with words and features, right? And documents, sorry, words and documents. So, we have 100,000 docs and a vocabulary of 50,000 and about 2,000 words per document, right? And so we have 3 classes: sports, mystery, aviation. So this is kind of an NLP example. So if you think about it, the word run appears 12% of the time in sports, 10% of the time in mystery, 2% in aviation, right? So you kind of establish that.
Yeah, and I realized what my mistake was is you're just doing proportions because you're computing the probabilities based on your data set.
Okay.
You just need proportions. I don't need actual numerical features for these. That's what my fault was.
Okay, so you answered your own question, you mean?
But
Okay, yeah. So since I'm here, so this is Bayes' theorem, right? And that's what you want to do is that. For 3 classes, you do each argmax of given the document, is it this class or the other one? And all of it is based on the frequency of its occurrence. Simplify this a little bit, right? And bag of words approach, which is your one-hot encoding that you guys call, that's kind of what it is. So it's the probability of the features, right? So every single feature has a contribution.
Okay, so there's probabilities, not the actual feature.
Yes. And so now you end up with that. So the probability that you saw that feature with that class. You see that? All right, and so that becomes a multiplication over here. So for class C, you kind of figure out what is the probability of the class overall, and then the probability of each feature associated with that class. And that's just a frequency count. So how many times have you seen that with that, that correlation? And so then just to calculate these, they're just counts. So you can see that there. Does that make more sense? Okay, great. All right, so we're in the break, guys, so you can relax and then continue.
Can I just ask you?
Yeah.
I just ran this and I want to shade the result, make sure I have this right.
Sure.
The 2 things I think changed, like the inference function. So instead of having this inference with deep layers, I took it from the other one.
Yeah, you just look at the inference and the loss.
So
That
the
should be
2,
correct,
and
yes.
I modified down here, I used this inference
That
and
should be it.
loss. Okay,
Yep.
that's it.
That should be it. That should be just a
Basically the
logistic
same.
regression.
Yeah, wonderful. This is the first one with the deep bound. This is one which is.
Okay. Yeah.
Okay.
Yeah, so you can see it learned a little and then it became
Then it-
pretty good. Yeah.
Okay, great.
Yep.
I think my underlying question, though.
Oh,
and
okay.
I bet it was a formal step. I should have reminded remember who it's counts.
Okay.
So for example, K and N.
K.
Is like, is it just, what is it, these things are categories, so they're important stuff. I'm getting
Sure.
on how it's treated.
But I still think there's no underlying conversion going on. I still think, because my interpretation, you guys had this issue of source port 22 and 23 are not related at all, right? That's what you, but the way that I interpret that feature is more, because there can be other interpretations of it. For somebody that doesn't know anything about ports, they just might say the low ports, 0 to 1000, maybe have some meaning. For instance, I can make it a scale by saying importance versus less importance, if that makes sense. So so in that sense, it's a scale that maybe it's not linear in a sense, but from 0 to 1,000, not important, right? They have some meaning. Whereas it starts to go up, maybe less important. Do you see that? So that may be what KNN does. It treats it that way.
It's just, and maybe it's like stupid to get into it, but it's just something where like, you have to have a distance function. So on
Yes.
protocol, there's no distance functions, they're just strings.
Yeah.
So I can define a distance.
On protocol,
So there
oh, they're strings you said? Where are they strings?
HTTP. So they're numbers, right? We can't, but the way they're recorded in our data is.
Are they really words? In edit, go to edit. And look for that column.
Yeah, I see. So that's what I mean, they're not in a space we have to.
Yeah, I see.
And I can measure them as words, but that.
For something like this, I do believe Weka will probably convert it into a number if it's KNN. That's what I would think.
And so that's why I was like, how do we do that?
Yeah, I don't,
That's getting into the weeds.
that's a good question. I've actually never even thought about it.
Or it could just be monopolized.
What I can tell you is sklearn and Tensorflow will not like it.
No, because you need to throw those out.
You have to use the label encoder to make them into numbers. And then okay, I see. So in this case, you're right. There might be something under the hood.
Yeah, I'm not a super Craig. I just don't know.
Yeah, I don't know either, to be honest. So, yeah, I see your point. I'm sure there's some other stuff. If anything, it takes the character, it takes the hex of it, which gives you like the equivalent ASCII number of it, and makes a number out of it, if anything.
Well, there's all kinds of distance functions I have for.
Yeah.
Kind of distance.
So it could be something. Yes. The food tomorrow? Yeah. Guys, so as far as food tomorrow, the same thing as this morning. That worked? It seemed okay. Yeah.
For breakfast?
Yes, sir.
Can we get a chef out?
Chef.
Unless
I don't know. This is my department head that just keeps asking this. So. Yeah, the same. It's the same.
And can we have something else besides just vegetable fruit? Like we have maybe some veggies and some donuts or something like that?
Don't. So they want donuts too. So just let her know. Throw in a few donuts. Hey, I don't know. I'm pretty sure they'll do it.
Frozen donuts sounds great.
Awesome, thanks.
Because if we have donuts once, then we need
They were significant.
coffee.
All right, so just keep working on this. I mean, if you have any questions, I'll give you guys, at this point you can put your skills to the test. Hopefully that'll bring up questions. All right, I would recommend that you try to get a deep neural network also to function, right? So there's that code example I provided when we started today. So maybe you can even get that going. All right. questions? So if someone has finished, you know, raise your hand. Just let me know that you've done
How
all
much longer are
three.
you going to give us, Bill? How much longer are you giving us?
How much time?
How much more time are you giving
I
us?
can, you know, I was planning just to leave like 1 hour for the last set of slides. So.
So another 10 minutes.
Oh yeah, we could
Another
probably go to 3:45. We could go to 3:45, for instance.
Okay, so we got some time.
Yeah, you have about, if you want, I mean, you have about, you know, 25, 30 minutes.
Okay, good.
And then that way, we just have one slide. We finished the slide, this one, linear to logistics. So we really just have one more slide for today. So the last hour, basically, should be enough. Questions here?
What
Question?
time is the break until?
3:15. So.
Oh, okay, so we're done. Okay.
Yeah. So we could probably, you know, just continue working on this until like 3:45, and then the last hour we have one lab collection.
Okay, thanks.
which I print things make a difference?
Does the order in which you print things? Which things?
I mean, the order, if I print something before doing like the Y true, I'm trying to isolate this, do only print if it's like every so many iterations. I'm getting like all zeros.
So you're trying to print.
So I moved all the non-printing stuff to the top, and I want to print only every like 100 iterations.
What do you want?
Print like the accuracies.
Oh, okay. So that should work. I mean, printing the accuracy, right? But first you have to run the eval, right? And it has to give you a result in this.
So
And then you have to run that through. You have to print that metric.
yeah.
You have to get changes. So that one actually has a print statement.
Yeah. Does it do non-printing things?
Look at it.
Prints that metric.
Yes.
Yes, definitely. So the accuracy F1 recall and position.
So we could say. I could say.
You'll have to modify the function.
Yeah.
Oh, I see what you're saying. You don't. Oh, I understand. You don't want to print every iteration the results. You just want to print it every 1,000 times.
Yeah. So let's say.
You can pass the index.
So I could say print equal false.
I think something easier would have been.
So I could say what I do here. If
You're about the same.
print. Okay, print. No, it's print results. Let's call it if print results. And we'll do that unconditionally.
Yeah, I see what you can do that.
This again will be if print result, if print result is true. And this will have to be appended unconditionally.
Oh, it's this
And
there.
if print,
This needs to be in the.
what?
This was not.
Oh no, you're leaving the. Okay, so that's the print statement.
We're not actually.
So are you doing it so every 1,000 you're printing?
Is that 100 for now? Okay, let's see if this works. It's all zeros for the predicted. The predictions are all zeros for some reason when you do this.
Okay, so it's not learning.
It's always predicting zero.
So that tells you that it's not model. So go back.
Well, it's always
Your accuracy is 50, so
because it's always predicting zero.
scroll down. write it with the law, with just, not the neural net, but with the regular logistic regression, what does it do? Does it actually learn? Where the position is still zero?
Really was language exercise aspect. It's just as a yeah.
There, now it is working.
Yeah, so it's something with your neural network architecture. That was not correct. It's doing really well, actually. Right?
Yeah. To do the graph every 1,000 and for every 100. Oh, now it's got 3 incorrect. After 1,000, now it's back to 2. So it did start low, then it went up. And went from 3 back down to 2. Now, what is it now? Thanks for helping.
Yeah, sure.
Try to myself, yeah.
All right, great. Any questions over here? Questions, guys? Yeah.
Do you have any offense when I say roll tide?
Huh?
I'm joking.
Okay.
Did you get it?
No.
Roll tide? Hello, stay with me.
Okay.
We just play each other this year. I will remember to see you now.
Okay.
No, y'all don't lose, so it's okay. It's not personal.
Okay. All right.
That keeps you humor. You can take a break. You laugh a little.
Yes.
Yeah, you heard me laugh all the time.
Right.
Yeah. See? Okay, so see?
Yes.
You just been here today. So yeah. See, at least got a laugh.
Questions? Guys? All right.
Any questions?
I started doing was playing with your code and
See ya.
changing the number of times and let's see where it converted,
Mhm.
where it actually stops. So first I ran all 5,000 because
Yep.
it was, I want to see what it was supposed to.
Sure,
Sure. Okay. Then I dropped it down to 500 and it converted from about 25 something.
Okay.
And I was like, that's nowhere near enough.
Iteration, okay.
Exactly. So I said, let's start incrementing by 500 and see how closely I get to.
Okay.
Quickly I get to 1. So basically it was 1,000, but it's still not 1, but it's close enough.
Right, right,
So,
okay. Great.
So that's where I'm at now. Just,
Good.
so like you can sort of see what the numbers look like.
Mm-hmm.
So
Yeah, they're pretty good.
yeah, but so I'm trying to think of exactly what numbers about it. You know,
For the-
iterations. But this is
Yeah, so here it's an easy problem. With a more complex problem, it'll always be like 70, so maybe you give it a lot of iterations and see if it's a problem of just looking, you know, having more epochs.
Yeah. So that's what I was thinking
Okay.
at this point.
Great. All right, so it's 3:45. So do you guys think you had enough time to work on that lab assignment? How many of you completed the WECA part? All right, so what about the sklearn part? All right, good. So it seems. And what about the TensorFlow part? How many of you actually got something out of that? All right, a few of you. So what did you get? Did logistic regression? Did you get that to work? What about the a deep neural network or a neural network? Did that work for anyone? Anyone get that? No? In the back, what's his name? I thought you had it. Matt? Did you get the neural network to work? You had some results, right?
Yeah, I did.
Okay. And they were pretty good. So no one else was able to get that part to work?
Mine just came up with actually
50%, okay. All right, but logistic regression did work for most of you. Okay, great. So that's great. So at least you played around with neural networks. We still haven't done officially like the lecture of that, right? So I need to, hopefully once I explain that layer and the architecture, it'll make sense for you. So that's tomorrow, right? So that's basically.
Played around with the code you gave me.
You played around with the code. I saw that it worked for you.
Yes.
Yeah.
Well, the code worked without any modifications.
Right.
But the print wasn't the best. I had to clean up the code so it would print nice.
Yeah, good job. All right, so so that's good. So all the results were good for sklearn, WECA, and at least logistic regression with TensorFlow, right? Most of you got like 100% accuracy, right? All right, so that's good. So you got to practice with this. Tomorrow you will do IoT. You'll do IoT, malware, in TensorFlow. You're going to do the actual KDD, the whole set. For that, we're going to need like our GPU boxes. And you're also going to solve 2 new data sets, right? Phishing, this one, and you're going to solve the fraud, credit card detection fraud. Now, some of you requested a more difficult or noisy data set, so I will provide something like that as well. So there will be one more data set tomorrow. All right, so the plan for the afternoon, hopefully, is just to work on labs. In the morning, we'll do that AWS GPU 1, all right? So, which actually you'll barely notice any difference, right? And that's great, right? So that means our code just runs in the GPU easily. I will do, of course, the lecture for the neural nets and deep neural nets. So hopefully that will get you that extra knowledge so you can apply deep neural nets. All right, so it seems like everyone got this to work. One thing that I would have recommended is that you do the feature ranking also in WECA. Did anyone do that by any chance? And what did you get as the best features? Did you get any insight there? Those of you that did it?
source bytes was the best.
Source bytes. Yeah, there you go. So that's, remember, it's just a statistical correlation. So yeah, I would imagine if you're studying now, you want to know why, you would dig in deep, right, and figure out why that is the most important feature. All right, so are there any questions about this data set? So obviously you've had an opportunity now to read, instead of always reading one data set and splitting it there, you now have code also, that might be more realistic for your examples. You always have train sets, right, and then you have new test sets that you're providing in separate files. So that gives, this exercise gave you that knowledge as well. All right, are there any questions before we move on to the next topic? All right, it seems like everyone is clear. So the last topic is a little bit more intuition, I would argue, about logistic regression as we start to make the transition, right? So remember, we're still kind of intuitively at linear regression, all right? And now we want to make that jump to logistic regression and classifier. And so hopefully this example, it's not a math proof. Again, it's more of an intuition, right? So there's got to be some jumps that you have to make, but even if you don't believe what's happening, you can see it in the code, and that's what's so great about it. So you'll see in the code that you'll use the so in logistic regression, you basically use the same inference function with some modifications. All right, and so that's what we're going to look at. So let's open up the last slides in logistic regression, which are these. Okay. So I'm going to open it. All right. So this is now logistic regression in TensorFlow. All right, a little bit more of the intuition, if you will. Intuition. Okay, so the learning outcomes here, a little bit more on the theory of logistic regression. So not the math intuition, but just intuition in general, let's say, and a little bit of aspects of the code. So the idea is now, of course, whereas before we only had this machinery, right? That was the machinery that we had initially. Now we've added a new label or a new neuron, right? That makes it now, we have two things which allows us, because they are going to be one-hot encoded, they allow us to create the classes, right? Like that. So this is the jump that we have to make. All right, so neural nets. So before we look at the deep neural nets, it's a good idea to look at logistic regression. So logistic regression is still a linear classifier, right? So it still creates a boundary that's still linear, right? So remember, that means it's still doing that. But deep neural nets can build on the ideas of logistic regression. So basically, here we will use all the code that we have developed so far, right? And now we can just make some modifications, in particular to the loss function and to the inference function. That's the only place where we need to make changes. And I've set that here, so we only need to change these two functions. So as we can see in the text code segment that we had before, inference is mainly different for the logistic regression. Inference is mainly different from the linear regression approach, because we now run our equation, this equation, right, through a softmax function, or let's say a sigmoid function. So some function, right? And that function is going to modify the values that we had into a specific range, which is going to be 0 to 1. Do you see that? So we're gonna take, as I said, imagine the sigmoid over here, right? Any value for this, remember this is y, right? Any value that we get there, 250,000, 290,000, and it's always going to be constrained, right, to this output, right? 1, 0. Okay? And that's just a straight up sigmoid function. Okay, so we take the same equation from linear regression, and now we apply it through a function called the softmax. So the softmax is actually a little bit beyond the sigmoid, right? So there's one additional condition there, and we will see that with an example. Additionally, instead of predicting real valued numbers with just one output neuron, we now have several output neurons, which will represent each possible class. So for instance, for iris is 3 classes, for mness is 10 classes, right? Handwritten digits. So now, here is where we kind of want to think about this intuitively, right? So let's see if this makes sense. So housing price, let's start there. So for the linear regression problem, we were predicting housing prices. So we were predicting housing prices given square footage, right? So we had square footage over here, and then we learned W and the bias, and that gave us the housing price, right? So that's basically equal to this equation, right? Which is really y mx plus b. That same equation that we've seen throughout this week. So this formula with values would look like this, right? This is 5,000, the square footage, and these are the parameters. So this is the bias, that's the W, and that should give you this predicted housing price. So the model learned the parameters 50 and 500, right? So that's what it learned. And with an input of 5,000 square feet, it can predict a housing price. If you remember, this is a network of one input neuron and one output neuron. So you have something like this, right? But the question is, how can we represent a model of several classes, right? Because we know that's where we're going now. You know, we can't, this machinery does not help us for our purposes, right? So we want to actually represent multiple neurons. So, such as a model of the iris data set, which represents 3 classes. So we just kind of have to think differently. So what, you know, we can basically decide, okay, we could build, we have this initial 5,000, but that 5,000x could predict other values, right, if we had other parameters. So other W's and biases. Do you see that? So you can see that here. So if one predicted, let's say, 250,000 with one W, one, let's say, or this would be 2. If we figured out another W, another W, W1, right, plus a bias over here, we could get 150,000. Do you see that? And we could do the same with this one, W3, we can predict 300,000, or 350,500. Additionally, we can take another step and say, well, usually what we're saying here is that we have a low-priced house, a medium-priced house, and a high-priced house, right? So this idea actually then starts to tell us about categories, right? So whenever we get this value, that's low. Whenever we get this value is medium, and whenever we get this value is high, right? So we could make that intuition already, right? That those prices represent, you know, categories. So we are going to have to use activation functions for this, like the sigmoid function. So here's another like element that we throw into this equation. So we know in linear regression we can learn to predict real valued numbers given inputs. All right? And then for math, we also know that we can run real valued numbers through certain functions to obtain scaled versions of those numbers. That's something we just know. Right? So if you think about it, it's like somebody started to build a machinery and then adapted that machinery to learn, right? To learn different things. So in this case, a function such as a sigmoid, or in more specifically, more correctly, the softmax, can do the following. If I had my y, right, which is that linear regression equation, this one that I just learned, right, and if I run it through the sigmoid function, I get a new y, right? That we've established. So then you can do something like this. This function will take any value and convert it into a value in the range from 0 to 1. You see that? So for example, we take this equation, whatever we get here, right? We apply it through the sigmoid function, and now the new y is something in the scale from 0 to 1. Do you guys see that? And that's just the basic math mechanism. So that already tells us, well, we could, you know, that inference function that we had with the y equals w times x plus b, now let's run some sigmoid function. Now our outputs are going to be values in the range 0 to 1. Guess what? That's important because you have values in the range 0 to 1, and now your labels are going to be 0, 1, 0. Do you see that? So it's also values within that. Okay? So the softmax function, this function, allows us to learn functions that predict values between 0 and 1. And this is good because these values can also be interpreted in a way as probabilities or strengths of my prediction. All right? Because, you know, now instead of giving it the housing prices, you're just going to give it the equivalent interpretation of that. So if you want to think of it this way, instead of me giving you 250,000 or 150,000 or 400,000, you simplified it by saying, I'm going to give you the high price, 400,000, so that's 001. Do you see that? So that's what you're giving it to learn. right? And so by building this softmax conversion, you can actually learn those numbers. All right, so as in, and this can be interpreted then as I have an 80% confidence that the housing price is 250,000. So it basically means that that was high, the other ones are low. So it's really 0, 1, 0, right? So that's the interpretation. So let's think of it a little bit further. So what if I had 3 possible housing prices, these 3? How can I represent this in the previous equation? So here we have this. So if we built one equation for 250,000, we can definitely learn equations for the other 2 prices, right? Do you see that? So here we have 5,000 is the x. Notice it's the same for everyone, right? So they all share the same x. They just have different w's and they have different biases, right? And that's what allows you to predict different housing prices. So now, whereas before we just had one network like this, now we have 3 separate networks, if you see that here. But the 3 separate networks now are x, 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 w1, and predict individual y's. Right? So we can actually then structure that as a neural network of this architecture. So now we have one single input, right, that is tied to 3 possible outputs. Do you see that? And that's the same because it's W1. So actually I'll do 5,000, 30, 50, 70, plus, 700, 500, 400. Do you see that? That's this represented as a network here. Remember that each neuron is dependent on, what is before it, right? So this neuron only cares, about this input, really. That's it. There's only one input in this problem, the square footage of it. All right, and so once we have that, then, so now if you notice, we have created a system of 3 equations, one single x, different w's, different biases, and different y's. And this can be modeled as a network. You put it together. So if you look at this as a network, we can see that it has 3 output neurons, 1 input neuron, and in fact, the network will look like this. And there you have it. So it's actually a neural network, but combining 3 linear regressions, right? This is still 3 linear regressions. There's nothing here about zeros and ones yet, right? So hopefully that's clear, right? So we build this, we give it this 5,000, it learned this W and this bias, it's going to give you that housing price that we have. Okay? So we can build that. So still not what we want though. So now we also know if we apply our sigmoid function, right, to y, then we get a new one, a new value. All right? So to each equation, then we can get, each one of these predicts y, apply it through a sigmoid function, and now we get a new set of values. All right? So instead of the 250,000 or whatever they are now values scaled to somewhere between 0 and 1. Okay? So a new set of outputs which are now scaled to be from 0 to 1. So this should be our. So our formulas that look like this, right, now can look like this, right? So now they can be modified to be within this range, values between 0 and 1. Now the values that we will give them are also between 0 and 1. It doesn't matter that we're not going to give it 0.5 because remember, the mechanism can learn those values. It's just going to ignore the ones in between. You see that if you gave it 0.5s and things like that, it would also learn that. But that's not the objective. So you give it zeros and ones, and it learns those values.
So the fact that those add up to 1 is not relevant?
They don't add up. They don't add. Okay, so that's a good question. So I haven't introduced that part yet. These add up to 1, but technically, with what I've created with sigmoid, this could be also 0.7. So they don't yet add up to 1.
So that just happens to that.
I should have written here 0.7, 0.7, 0.10. Because I haven't yet introduced the fact that they should add up to 1. Right? We're almost there, but you're right. So currently these values don't necessarily add up to 1. Because all we did is I applied some function, and it predicted, so far, 0 to 1. Everyone with me? Okay. So this intuition hopefully shows you how you can train models to predict confidence of a specific output neuron, such as confidence that, given a square footage of 5,000, the housing price is more likely to be 250 based on that confidence. So it learns that class and not the other ones, given the training set. And also, the intuition is to train this model, you do not need to give it the housing prices, but just the output neuron associated with those inputs. So it's like saying, instead of 250,000, now you're going to say 1 for that and zeros for the other values. So now you have the machinery to learn that part. So that's what I'm saying. So you can see here, in this case, our X matrix would consist of one sample 5,000 associated now not with the values, but just with 0, 1, 0. Right? Because we give it 0, 1, 0, the model predicts values between 0, 1, 0, so it can learn them. Right? It can be trained. Right? So you give it actually this value. So now the softmax, right? So formally, a softmax function is a way of mapping a vector of real valued numbers in any range into a vector of real valued numbers in the range of 0 to 1, where all the values add up to 1. Right? So that's what you were getting at. So we need to define that, and we don't define that with sigmoid. We define that with softmax. All right? So the softmax function. So the result of the softmax, therefore, gives a probability distribution over several classes. Right? So you can see that. So it's going to say 0, 1, 0, which might be 0.3, 0.3, 0.4, 0.3, right? So this one, the most likely one. Right? But that's what the softmax actually does. All right, so now let's see how that works. Right? So the softmax function can be written as follows. Right? So this is basically, the example. So it uses exponentials, right? So we calculate. I have a Python example here, but we can see it here. So I give it something like this, and it's going to map the values to something like this, right? That's sum to 1. So instead of me saying it in words, let's just do it in Python. All right, that'll convince us that this actually works for vectors. All right, so I'm going to go over here. All right, so let's go back to our Python, to our VM. All right, so let's do Python. All right, so let's see that we assume that we ran these values, the so-called logits, right? 2, 1, so we do 2.0, comma, 1.0, comma, 0.1. Okay, so those are our values. They don't add up to 1. 0.1. All right. Now let's import NumPy as NP. Okay, so what we want to do is we want to take all the values and raise them to an exponential. So we're going to do exponentials list is going to be a list comprehension. So we're going to do np dot exponential I for I in logits. Do you see that? So we take every single number, we raise it to an exponential, right? That gives us the exponentials. that gives us the denominator that we had in that equation, right? So we're going to add up all of these. So the sum of exponentials equal the sum of these three values, right, that we created in exponentials. So I'm going to do exponentials like that. All right, we can also print out exponentials. We can see that's what happens to the values, right? So the three values were raised to the exponential. We add a map. That's the term in the denominator. All right, the sum of exponentials is the denominator. Sum of exponentials. That's the value that we've computed as well. And now we want to figure out what softmax would output for all of these, for each individual one. So we're going to do softmax equal j divided by sum of exponentials, right? And just, it's a list comprehension as well, so we do 4j in exponentials. All right, so you see that? So we basically computed that term that we had in the equation, and now if we print the sum of softmax, hopefully it'll be equal to 1. And there it is. So it is equal to 1. So this is the actual function that gets applied to your values. All right, so that makes it so that the values are now equal to 1. So you can see that here. We go back to it. So it wasn't the, so if you didn't, maybe a little bit confused with that, remember, we applied the sigmoid function, right, to each individual housing price. The problem with that is that it did not give us values that added up to 1. So we really actually needed to apply the softmax function, which is this one, and that one ensures that the values will now be equal to 1, so they can be better, more easily, I guess, interpreted as probabilities, because they all add up to 1, basically. All right, so this is the machinery that you build on top of this, right? So now you're going to get whatever your y's were, but whatever that value is, it gets transformed into values between 0 and 1 that add up to 1. And I don't know if you realize, but that then allows you to train, given zeros and ones, it allows the model to learn that. So remember, the models learn whatever you give it. And in this case, we created the machinery to learn zeros and ones. Right? Because remember that at the end of the day, the zeros and ones represent, I'm giving you this. I'm 100% confident that this is a medium house price. And I have 0% confidence that this is a low house or a high house. Do you guys see that? So again, that's the machinery. And it's straightforward in the sense that you learn the W's, you learn the biases given an X. It produces some Y, but the Y has to go through a softmax, and that softmax produces a vector of probabilities that sum up to 1. Right? That's what the algorithm can learn. The classes that you give it are 0, 1, 0. You're saying, 0 confidence is class A, 0 confidence it is class C, 100% confidence that it is class B. Right? And so it can learn from that also to predict values, because whenever I give it in the features lake house, front view, ocean view, high school district, a lot of square footage, you also tell it 0, 0, 1, right? You're implying that's a high-priced house. The mechanism that you have in between takes that X times a W and a bias, predicts some kind of Y, but that Y goes through a softmax function that is going to predict the probability, 0.2, 0.2, 0.6. And the 0.6 then translates into being 0, 1, 0, for instance. All right, so this is the mechanism, and this is what we will see when we look at the TensorFlow code. So if we go over here, and we did this already, that's the Softmax function. Sigmoid, by the way, I don't know, anyone remember what sigmoid is? I think it's something like 1 plus e to the x. Anyone remember? But it's something like this. And so that's why these are exponential, so you can look it up. All right, so, that's, like, looks like Gaussian also. All right, so I said this explanation, right? So hopefully that was a little bit of the intuition. Now let's look at this in the code, right? In the code before, simple linear regression defines the network architecture as such. So we have TF matmul of xw plus b. Do you see that? xw plus b, where we have the w and the weights and the biases initialized to some zeros matrix. All right, that's linear regression. Logistic regression, if you notice, logistic regression defines the network architecture as such. So what do we have here? The same w and the same bias. Nothing has changed, right? We define, the parameters basically however they were before. And this, if you look, is exactly the same equation that we had in linear regression, right? It's w, it's x, it's x w plus b. So that's the previous one. xw plus b. A matmul operation, except this predicted a real valued number, right? And our architecture was very simple. We just had that. Now we have the complex architecture of A and B here, right? So we're taking into account the number of features in the input layer and the number of classes in the output layer. The additional component now is that we need to run this y through tf.nn.softmax. Do you guys see that? Now in the previous example, the output was just one neuron, right? One neuron. In this example, the output is actually B neurons, right? B neurons. Because this is where you define the architecture of this model. Yes, sir. Go ahead.
So is the NN for neural network and tf.nn.softmax?
Yes, that is for that's where they put it. I don't know why they put it in neural networks, but it's a straight up softmax function.
Softmax can be applied to anything that's
Sure, it can be applied. It's the code that I just showed you, right, in Python. That's literally it. So, I mean, I don't know how else to say it, right? Think about it. You still have a weight and a bias. You learned that as part of the model. You multiply that times the original x, right, the inputs. That produces a y. You can see in the code, the only new additional thing is that now these are going to be constrained into not just, like 250,000 over here. So they're not constrained into 250,000, but instead these are going to be constrained into 0, 1, 0. Okay, because there's those multiple nodes. Okay, but also I guess you could say, if that confuses you, just it'll be constrained into something either 0 or a 1 for one neuron. 0 or 1. All right, and so that's the only extension that we have in the inference function. Everything else is just defining the W and the B. Here is also, someone had the question about the initializers. Here we have a different initializer. So now we create the variable W with init, and init is just a different kind of initializer. Or another way of, maybe now instead of zeros, we can put all 7s there or something like that. Still not normal, but it's still another way of initializing things. Are there any questions? So that's ultimately the change that has been made to the function so that logistic regression can predict values, from 0 to 1, which are the one-hot encoded values that we have. All right, so this function, think of it in another way, this function can only predict 0, 1, 0 or 1, 0, 0 or something like that. Maybe think of it that way. We built the machinery by constraining it with softmax. We can only learn this. We can no longer learn 250,000, 350,000. We can only learn 1, 0, 1, 0, 0. Only. Why? Because by making it softmax, it needs to add up to 1. Right? So, 1 is going to be usually dominant. Right? So this can build that, and we don't complicate things because we never give it 0.5, 0.7, right? What do we always give it? Zeros or ones. Do you see that? So in a sense, we built the machinery to predict zeros and ones, and we also only give it to train zeros and ones. And so at the end of the day, given an x, given the zeros and ones, given that the model, given those things only predicts zeros and ones, it can learn zeros and ones. Right, so hopefully that makes sense. So maybe the way I said it just now is a little bit more clear, right? You give it the x's, learn whatever w's and b's, or let me say it in another way. I randomly assign w's and b's to that x, right? I do that. What does it predict? Randomly, zeros and ones. It'll never predict anything else, right? And so it can predict the zeros and ones. You give it zeros and ones, so now it's the other way. I give it zeros and ones, that determines the w's and the biases. So it creates a correlation between inputs and zeros and ones. And that's how it works. So hopefully it makes sense, but it's kind of elegant. It's basically the same exact mechanism, just that we force it, if you will. We are forcing this model to only learn zeros and ones, and then we give it zeros and ones, and it's going to adjust the weights to try to predict those same zeros and ones. All right, so that's logistic regression. So, and this is kind of the model now, right? So we have 4 input neurons and 3 output neurons that we have there. Okay. So let me see what else is here. Oh, so there's this part also. So that was only the inference part. So are there any questions about the inference part? All right, so remember, and I'll repeat again, in the inference part, we took the linear regression, constrain it through softmax. We build a model now that only learns values between zeros and ones. Given that everything is labels now, which are zeros and ones, it'll correlate those to the inputs and adjust the weights accordingly. Okay? So that is the inference, and hopefully that made a little bit of sense. The next one is probably even harder. All right, so this is the loss function. All right, so the loss function is now, remember, with linear regression, it was intuitive, right? What was the loss function for linear regression? Least squared errors, right? Least squared errors. We know that, right? And so now the loss function for logistic regression looks something like this, right? It's another function, right? No longer that, minimizing the sum of the errors, right? Now it's something like this. So that function actually can be interpreted as this graph, right? Have you guys seen this graph before for logistic regression? All right, so the objective here is to minimize cost, right? So if you notice, there were 2 conditions for the function. There were 2 conditions for the function. If the real value is 1, then this is what you want to minimize. If it's 0, you want to minimize this, right? So intuitively, that means here, What is H0x? It's the inference function that we learned, right? Would you agree? So the y equal mx plus b run through softmax. Oops. Let's just say run through G. That's what that is, right? So this is dependent on the m and the b. So that equation is dependent on the m and the b, right? That's what we learned. So if I learn, let's say randomly, really bad ones, right? Or some set, not even bad ones. I learn m plus b, right? With this function, if those values come out to here, that tends to be very close to 0, correct? Do you see that? It's close to 0. But this was, the real one was what? 1. You don't want that, right? What do you want if the actual is 1? You would want the predicted to be close to 1, right? And so you would want it to be over here. You see that where the cost is minimized. So that's what this function captures, right? Is the relationship between the real and the predicted probability. So that's why this is a type of a logistic regression probability loss function. All right, so I'll kind of repeat this again, right? So remember, this is the function that you learn, right? That's the function that we learn. And so this function, right, if with one set of parameters, it's going to predict either a 0 or a 1. Do we establish that? It predicts a 0 or a 1. So if the real value is 1, then we want this value also to be close to 1, right? So it has to follow this relationship. So we would pick those weights as the correct weights. But if the set of weights that we picked for the function come out over here, right, that means that this predicted value is closer to 0, which is not what the real one is. Okay, I think I saw a nod there from someone. So that's kind of the intuition of this approach. In the least squared errors, it minimizes the sum of the errors, right? Y pred versus y actual, minimize that as a distance function. This is a different one. This is more like it doesn't predict two values and you calculate the difference. Here you predict a 0 or a 1. So the function that regulates that is this one, which is represented by this. So this is just a fancy way of saying that this creates that one and that creates that one, right, in the loss function. So again, let's look at the other side. Let's look at the other side. So again here, remember maybe if I draw y minus y hat square, right? This was, again, pred versus actual, except that we were doing 37 and 32, some real value number because it was linear regression. This one only predicts 0s and 1s because we constrained it with softmax. And so remember, this function is g softmax wx plus b. We learned some set of parameters that outputs either a 0 or a 1. We also want to compare actual to pred. And so the actual here is 0. The actual here is 0. So our goal is for them to be equal, right? So if this function, if the set of weights w plus b predict a number closer to 1, this function will penalize it. Do you see that in the objective function? So the gradient descent algorithm does this. I pick some values. I picked a 0 value. I map it into this function, and it's going to tell me if it's close to the 0 or not. Right? So over here, if the function picks, you give it this and it predicts a 0, right? Then it's going to say that that's the thing that you want. Now, maybe one last element that's missing is that here in this function, you provide the actual real value, right? So you're going to choose which one of these graphs to use. So for instance, if I say that the real value is 1, right? then what happens to this side? 0, right? It tends to 0 because 1 minus 1 is 0. Therefore, this function is that. And that's the thing that you optimize, this behavior. This behavior. Now, I'm going to do the other example, and I'm going to say 0 is the real label, right? The actual label. So I plug that in here, correct? And in the other place. So if I plug that here and I plug 0 here, what happens now to this equation? 0 times whatever that is cancels this one out, and now you're just left with this. So for 0, this function here represents this behavior. And that's the thing that you optimize. Which forces the model, as I said, because this is that little hx0, which is here, right? It's going to force it to think, okay, if I'm using now this one, right? Because you set the real value at 0, so I'm forcing you to optimize only this graph. Okay, then I need to, is that a good or a bad thing? Well, this function says that if the weights that you picked and the bias, those parameters, predict a number close to 1, guess what? This says that your cost is high. But your objective is actually to minimize this thing, right? So what does it do to the weights? It rejects them. Do you see that? Next time around, it's still, the real value is 0. So we still got rid of this. So it's still this graph, right? Another set of weights and biases, okay? We have to, this equation is this. So this new set of weights comes out closer to 0. That is the objective, is to minimize this cost. So then what is your conclusion about that set of weights and biases? Do you keep those or do you throw them away? You keep them, right? You keep them. So remember, that's what optimization is, right? It's you have a function associated with a real label, but here it's not a distance metric. So that's where we're getting confused, right? We think of least squared errors, right? Just a distance, the square distance between the two values, and minimize the sum of that. This is actually very similar. This function with its little behavior there just captures two different logics, right? Represented by these two graphs. Okay, so let's go back to one more time. Let's go back. Let's say the real label is 1. So 1. That means 1 minus 1 is 0. So now I get rid of that term, which means that the objective now is, because this was 1, to use that function. Okay, great. Let's do the same exercise. This h0x, right? That is g, because that creates, zeros and ones. We constrained it to predict zeros and ones. Is wx plus b. This wx and b's are the weights that the model learned, maybe randomly. That predicts a value close to 0, let's say, for whatever reason. It predicts this value. It's going to basically tell you, given this function, it's going to return a high cost. But your goal in the optimization is to minimize the cost. So you're going to reject those weights, or the weights and biases. So throw them away. Do another iteration. Still, the real label is 1. Okay, the real label is 1. And so you do this equation, it's still this one. Now you pick another set of W's and biases, another set of weights and biases. This time around, what does it predict? It predicts a value closer to 1. Because that's what this machinery does. And so when it predicts that value, it evaluates it in the cost, right? It's going to return a very low cost value. Given that your objective function says, I only want low cost, because we're going to sum all of these and pick the one that minimizes this thing. And so now we say, what do we say about these weights and these biases? These are better ones. Now, take it a step even further. I pick another set of weights and biases that return a value over here. That has slightly higher cost. Since it's an optimization, which of the two parameter sets is better? The one closest to 1, given that this is 1. So that's the loss function for logistic regression. So it's a little bit trickier because it's probabilistic, but here we were picking values. We just constrained it with softmax, and that gives us all the elements that we need. Are there any questions about this? So maybe think about it a little bit more. Might sink in. But that's really what happened there, is that we, now we have a different objective function, and we changed the inference function. And so given these things, we can now look at the code, right? So in the code now, whereas before, for linear regression, and remember I kept saying this is so satisfying, right? Because it's the exact same equation that we understand that we plug in here, right? In the logistic regression, you can see that it starts to capture a little bit of that equation that we had before. You can actually literally write out the whole equation that I had. As it turns out, you can, like numerical methods, you can modify it even further, all right? And so, but this is basically saying that we're using that equation, all right? So this equation over here. So as you can see, it gets a little bit tricky. So what's the takeaway from this? If we had to really, some of you, I guess, were very interested in modifying the objective functions. It's doable in TensorFlow, but it's hard, right? You really have to know kind of what you're doing. And so the best approach actually is just to use the built-in TensorFlow functions, right? And just to understand, what am I trying to optimize? Right, so there's actually a function in TensorFlow called Softmax with logics, I think, and it's the same thing as this. It's in your code. Are there any questions about this? Does it make sense? All right, so hopefully it makes sense. Think about it maybe a little bit more, but that's basically the idea. Different objective, because now we are only predicting zeros and ones because we're predicting labels. And we built the machinery for zeros and ones just by adding this softmax function. That's really all we kind of needed to do. All right? All right, so as I said, remember, I did say this was the hardest part of this whole thing. All right, going forward, the great thing, if anything, the great thing about this going forward is neural nets and deep neural nets will still have an inference function and will still have a loss function, but the loss function will now become pretty standard. It'll just be, because we're building zeros and ones, right? Neural nets and deep neural nets also predict zeros and ones, yes? So then it should be pretty much the same function. Do you guys see that? The same optimization objective. So now we have the framework for the optimization objective for all the other things, because there's zeros and ones. What the new thing the Thursday, tomorrow, is that now we need to go back to inference. And we need to add this idea of architecture, which I've already hinted at by, X is an input, not to Y, but now X is an input to hidden layer 1, where hidden layer 1 is an input to hidden layer 2, hidden layer 2 to hidden layer 3, and you can keep going that hidden layer n to hidden layer n plus 1 until hidden layer n plus 1 is equal to the Y. And you build the entire deep neural network that way. And there's one more thing, that you run all of these through a ReLU or some other type of activation function. you know. So it's a little, yeah. So, do you have any questions? So, let's see where we are. Now, one of the things that you'll see in the code, for instance, when you apply the function, is that now the function starts to become unstable. Right? The function became a little bit unstable by applying this, by the way it calculates things. So we actually have to do a few additional steps to kind of, make sure that we don't end up with n divided by 0, for instance, with this approach. And so this clipping thing does that. Right? It'll do something like +1 or something like that. And so this actually, I have it in here because this underscores the problem of using the straight up equations, is that they become a little bit unstable in terms of numerical methods. And this is why TensorFlow has addressed that issue by creating their own functions. The fact that they use their own functions mean that you're not going to get these unstable problems. Right, so this is mostly just to motivate the fact that we want to use just the built-in optimization function. Okay. So actually, that should be in one of our code examples. So if I go to the GitHub, let me see if I can find it. So I'm going to go to GitHub, and I'm going to look at, I think it's probably in this one. So let me see. Oh, there it is. So this is now going forward, whereas before we had basically that equation of the two shapes, right? And we have to write it out. Actually, this is the equivalent of that in TensorFlow. So tf.nn softmax cross entropy with logits. That takes in the output and the YTF, and that is the loss function that gets optimized. But you might imagine that inside it looks like, the equation, the example that I gave for logistic regression. So inside you have that, basically, only more optimal. Do you see that? It's still the same thing, right? It's logits, as we described it, softmax, cross entropy. And actually, this function, if you Google it, you might want to maybe Google the cross entropy function, and that will give you a little bit more background on the maths of it. Maybe you just want to do the proofs of it or things like that. But intuitively, though, that's the behavior that we are trying to achieve. It's unfortunately more like probabilistic kind of a thing, these zeros and ones. So if you give it a 1, you want to learn a 1. If you give it a 0, you want to learn a 0. That makes sure that you do that because it penalizes any weights that when the label is 1 and you predict 0, it's going to say that's not good. But when the real label is 1 and you predict 1, it's going to reward you, right? And it's going to say, because the cost is low, and remember that the objective of the loss function will be to minimize the cost, as is determined by that function. Questions? All right. So anyway, so that's pretty much it. I think from this point forward, where the loss function part is also taken care of. And so now all that remains is for neural nets and deep neural nets to go back to that inference and now do the last part of the layers. And that's it. So that is about it. That's kind of the conclusion. So this was more, as I said, the intuition of that new inference function that predicts zeros and ones, and the loss function that makes sure that the parameters you set, the weights and the biases, actually predict values close to the real value. All right. So that's really my my last slide for today. Tomorrow I only have one set of slides, which is for the architecture of neural networks and deep neural networks. Probably easier, and then just labs all day, problems. So hopefully you guys asked for 2 challenging ones, or one that I already had and one challenging, so I'll provide that. Friday, it's a short day, right? We're going to do obviously machine learning is not just supervised learning, right? So I'm going to do one on unsupervised learning, just traditional unsupervised, and then one on, I selected one popular and hot topic from machine learning, so I picked deep reinforcement learning. I believe actually that's very interesting, in my opinion. So this is my opinion. So I'll do that one, yeah.
So tomorrow, since we're going to be doing a lot of labs,
yes.
If there were some that we want to either try again a different way, is it possible we could have some time?
Yeah, I mean, as I said, I literally only have one lecture.
Okay.
Just to wrap, so if you see, we did linear regression, now logistic regression. You've tried that in your code. Tomorrow is just neural nets, how to build the architectures. Once I explain that and we look at the code, you should be able to apply all the tools. That's really all the tools for supervised learning. Let me put it that way. Those are all the tools that I have for supervised learning, and so it's just going to be a whole bunch of labs. And hopefully you get to practice now and maybe ask questions, or things will start to click a little bit better. And then even the big data part we're doing tomorrow, although it's not such a big deal. I mean, but we're going to try that as well. And then, as I said, Friday, just 2 more topics, unsupervised and reinforcement learning. All right. Any questions? All right, so I don't have anything else. I mean, it's 4:47, so you can ask questions, or we can, be done for today. Maybe read up on what cross entropy is on Wikipedia. That might give you a little bit more insight on this topic. All right. Yeah. Which slides?
I think you have an error on.
Oh, I do?
It's
Okay.
about their like I
Okay.
think you should have S, and if you need to apply this increment to this function, you should have S is right here. Second next one. Yeah, that's what
Okay.
So you need that notation.
Yes to all.
Yes.
Sure.
Sure.
Yeah. Yeah, go ahead, please.
Okay, so about the code, so you have this long function in there that had, the y times the, log of whatever, and then you have the other part of it, that either plus or minus, the next one minus y, times it, I'm talking about the loss function. Logistic.
Okay.
Logistic, right? We were
Yes.
just working through all that with the diagrams
Yes.
and all, okay.
Okay.
But when you write it in the code, there's no, 1 minus y, there's no, it's just the log, it's y, whatever it is,
Times the log?
Log, yeah,
Yes.
but it's all missing, it's missing the full equation.
I understand your question.
Okay,
So here's the answer as I understand it.
Okay.
People ran the actual equation that we have in the picture and
Right.
get some results.
Right.
but they found that they can just take a part of it and minimize that part, and that's equivalent. It's still stable, and it still provides good enough results. Do you know what I mean? So experimentally, they concluded that you actually don't need to include the entire equation, just part of it, and minimize that.
Okay.
Do you see
Okay.
that?
Well, no, but it's like it's really
I
confusing because you're looking. I'm seeing the math,
Yep.
and I look at the code,
Yep.
and I'm like, that's not equivalent. So
It's
okay.
equivalent, I think, to only one part of it, right?
One part of it.
One
correct,
half
correct.
of it.
One
So I-
half of the
yeah,
equation.
so if I go, here.
Yeah, this one. Yeah.
So it's the
not-
y times the log of the y
okay,
predicted,
yeah,
right?
Y predicted, right.
So
exactly.
that is
the first part of
the
the
part
equation.
of it,
The first
y
part.
log of the y predicted.
Yeah,
You
yeah.
see that?
Yeah, just the first part of
There's
the equation.
and the
not
other part
one.
is not included.
Right.
So
Correct.
I knew this question was going to come
okay.
up.
Good. I didn't want to ask it in front of everybody. but
You can add the plus, right, and do it that way, but
It's so small. that
it
the
turns
factor-
out
okay.
that if you only need to optimize one part of it, and you still get good results.
Okay, because I think what actually probably happens is it's so small, is what it is on the other side,
Mhm.
right? If there's sort of like inverses, and that becomes really, really, really small, so it's negligible. Then the other thing is
Yeah.
like, okay, so in that function, the other thing is it takes the sum. Can you go back to the code real quick?
Yeah, sure. Which
Okay.
which
the,
part?
the same code that we were just looking at.
This
that
one?
Yep. Okay, so then what it does is it takes the, I want to see where the mean was. Okay, it takes the sum. Okay, so we understand what that is. But then it takes this mean here, right on it?
Reduce mean.
Right, reduce mean. But what I was confused on is you're running that once and getting one loss value, right? So in the other code, is that meant to be just once for every y underscore tf? So if you go back to the math equation, because the taking this.
Yeah, thank you.
right.
See ya.
So, okay, so you have the 1 over m, which is your averaging function right there, right?
Mm-hmm.
So, I guess my question is this is done for every single y,
Yes.
not once for everything. It's just this is every single y you're running this loss function on and evaluating it, correct?
Right.
Okay, then I
It's
understand.
the
Okay,
sum
then
of.
yeah. Okay, then I understand. I just want to make
It
sure
makes
I was
sense?
completely.
Okay,
I just
yeah,
want to make
so-
sure I was completely understanding.
Yeah,
it.
so it's
okay.
the real, the predicted,
Okay.
and you sum all of those.
Okay.
It's just that sometimes you pick, think of it as using the whole thing, but it turns out it only picks one or the other. It picks one or
Okay,
the other.
yeah, right.
And you
Okay.
sum all of
Yeah.
those results, right? Remember that this just returned, in that little graph, it returns a high value or a low value, the cost.
Right.
And that's the sum of those.
Right.
So you pick the ones where that sum of the cost is minimized.
Okay. Which you're saying is it winds up being you just need the first part of the equation to figure that out.
And that's
Okay.
somebody concluded that.
Okay.
Yeah,
all right,
and
okay.
so.
There's probably some proof out there on it.
No,
but-
no, exactly,
yeah,
so-
I saw the code. I'm like, wait a minute, that is not a quarter equation. Okay.
Yep.
At least I know more now. Okay,
Yep,
thank
yep.
you.
Yeah,
Okay,
sure.
thank you.
That was funny. I have my moments.
See ya.
That was fun. My zoo crew. That's
So what's the plan?
my
What?
zoo crew.
Oh, your group? Yeah.
My zoo crew.
Zoo as in you're going to the zoo or you're just your friends? Crazy friends.
Crazy.
We're gonna say, if you guys are doing